Hello all, this is CREST hydrological model quick demo session. In this session, I'm gonna demo how to run CREST hydrological model. And most importantly, I'm gonna demonstrate how will you draft the control file, which will input all the information that CREST hydrological model needs for it to be successfully simulate the results that you need. First, let's look at the example basin that we're studying at. This is a basin in North America in United States, state of Kentucky. This basin is small, about 180 square kilometer, and this is our example will start. And what you're looking at here is called a DEM, Digital Elevation Model. About information how to get DEM from the internet, you can look up our user manual, or you can look our other basic training videos. DEM is one of the 3 basic input that you need for the hydrological model to run. And look at this one is your training package. In your training package, you'll see 4 folders. The first one is the basic data. Inside the basic data, you will see 3 basic files that you need. The first one you already have seen is a DEM, Digital Elevation Model. You need to get this data from some sources. Most of the digital elevation model are coming from remote sensing source. And there are global data sets for you to choose from the internet. In our other training modules, you're able to see how to obtain this data and how to pre-process it to use for the model. The second important data is the flow direction model. Flow direction model tells where water should flow from pixel to pixel. This data can be generated using GIS tools, either using QGIS that we are recommending, or you can use ArcGIS Pro, which is useful too. The last one is the flow accumulation model. A flow accumulation model is generated from the flow direction model, which is also a GIS tool to be used and can be derived from the model you get, the digital elevation model. So digital elevation model is a source. All other 2 can be generated using GIS tools. And how to pre-process the data and generating those data sets, you can find the step-by-step procedures in our user manual and our training videos. The second folder is the forcings. In these cases, we are just doing a very basic simulation. So for the basic simulation, we need 2 forcings to drive the model. The first one is the PET. It's a potential evapotranspiration data. This data can be obtained in multiple locations, or you have your local sources That would be great. The precipitation data. In this example, we use a North American weather radar data as an example. Based on your location, you can use the global precipitation data or your original precipitation data as needed. Precipitation data is the most crucial data set that is needed for CREST hydrological model. If your precipitation data has huge errors, your results will have huge errors. The errors will propagate through the simulation process. In this example, we are simulating about 6 days. So we have, this is 6 days of data at hourly time step from MRMS, multi-radar multi-sensor. It's a North American product. The third folder is a gauge folder, which records the gauge observation data for that basin. So the gauge data is not required. If your study area does not have a stream gauge or does not have a gauge reading, this folder can be totally empty. You don't need to do anything about it. Then the fourth folder is the output folder. That's where all the results will be stored. Right now it's empty, but at the end of this demo, you will see the results saved in this folder. The last is this exe executable file binary that you use to execute the model simulation. But before that, we need to draft this control file. Let's open it. Control file has couple of blocks. We call it blocks. Each blocks, you need to input the information that is required for the control file. And it is also required for the CREST hydrological model to run successfully. The first is the basic bracket. The first bracket in this block, you gotta input the directory of the basic data. For example, we're gonna put here the directory of the DEM. That is basic data DEM hydroshed.tif. The next is basic data DDM hydroshed.tif. The third is flow direction data, basic data, flow accumulation model, hydroshed.tif. Then the next one is asking what the projection system is using in this raster file. For the data in this model, in this demo, we're using geographic projection. So you write down geographic. Then it asks if your flow direction data is generated by ESRI method. Basically, that's referring to the ESRI DA method. If you're confused about what I'm saying just now, ignore it. And in our longer training video, you will know exactly what it means. In this demonstration, it is true. Then the last question asks if the flow accumulation model is generated from the flow direction model. In this demonstration, it's also true. Another thing to address about this basic bracket is that it supports the GeoTIFF datasets, which is one of the raster data type. It also supports other TXT-based datasets. If you have more questions about other supporting data types for the basic brackets, feel free to contact us. And also, you will have the information in our user manual. The next bracket is asking about precipitation forcing. Again, it asks questions about data types. So right here, we're going to type in the TIF, which it represents the GeoTIFF data type. Then it asks for the units. The MRMS data provides the precipitation data as millimeter per hour. Also, if you have other type of data sets, for example, it provides the precipitation data as millimeter per minute or millimeter per seconds or millimeter per month. You just change your unit and the CREST model will recognize it. Most commonly, we use millimeter per hour. It's also a good practice that you confirm your input data, what the unit is, and make sure the CREST model can read it. The next question is about frequency. Also, it means the time step of your precipitation data. In this demonstration, it is 1 hour. If you have monthly data, then you type in 1 month. You have daily data, then you type in 1 day. In this demonstration, our data is hourly data. Then the next question is about the location. Loc means location. That's its directory. In this demonstration, the location is forcings, precipitation, and now it's a name. Let's go back to the forcing folder. Let's check it out. So each data at each time step has its name. So the quick way to do this, you just copy and paste of its name. Because all the names the same except its time. And this is how you set it up. It's a precipitation data. That's how it needs to be set up in this way. And more details, you can read it from our user manual and our longer training videos. And then we come back to this control file we can paste over here. But because this time is changing, so we have to change the time. We convert to the year from 2022 to YYYY, the month July to MM, the date 25th to DD, and the 4th hour of the day we change to H in H. So this in this way, the CREST model will read every single time steps for all the precipitation data that you can provide. Now the next bracket is PET forcings, which is very similar to what the precipitation forcing. And also you can see the basic bracket doesn't have a name. The precipitation forcing bracket has a name. That means you could potentially set up multiple precipitation forcings and name it a different way, and it has different location, different data sets. Then you can pick and choose which precipitation data you want to use later on in the later brackets. But that's more advanced uses of a CREST model. We can teach you later about that. T forcing brackets. Our PET forcing brackets are basically similar to the precipitation forcing brackets. And you type in the data type, which is geotiff. The unit, in our example, is millimeter per day. However, our data, the actual data is 10 nanometer per day, which is not readable for the CREST. So how to convert that? We convert to, we made it say millimeter per day divided by 100. So it's given as actually 10 nanometer per day. That's the original source data. Well, sometimes that's something you have to deal with, is that your data source has different units. But if the CREST cannot read it, you need to convert manually by yourself, either through preparation of the data, or you can use this a simple way to correct it. So when you put divide by 100 days, that's basically the data will put in there and divide by 100 and convert it to nanometer, 10 nanometer to millimeter. The frequency of the data is daily. It's 1 day. And location of the data is forcings PET. And the name of the data, if you look at it, we have Pro ET to month, day, dot TAF. The next thing is about the gauge. So when I say the gauge data is not required, but if you have one, you need to put in the longitude and latitude of the gauge. In this example, the longitude is and the latitude is And the observation, OBS, short for observation, is the location directory of the CSV file. It has a gauge, and the next question is, do you want to output this data in your output results? The answer will be true. And the basin area of this basin is 171.976. And the unit is kilometer squared. But you cannot really put in there, so you can only put a number. But in CREST hydrological model, the basin area is always square kilometer. And the last one is OneCode. It's about the data assimilation. We can talk about that in other trainings. So you might want to ask, what if you don't have the observation? If you don't have observation at all, no gauge data at all in your study area, what you need to do is you need to create the gauge bracket. You can call it any name. And all you need to do is to put in the longitude and the latitude of the outlet of your basin, which is the final river outlet of your study area. In this demonstration, we have this gauge location, then we use the gauge location. Then for the basin in Kentucky, well, we're given basin brackets, so we need to identify, oh, this is a basin in Kentucky. Then what does it have in there? It has one gauge, which we specified over here. Then the next two brackets are the parameters. Parameters needs to be changed based on your study area. But that's a more deeper topic. We can talk about it in other training sessions. Then the second to the last bracket is a task. So for task, you give this a name. You can call it KY simul, or you can name whatever. I always name it as simulation, which is separate from the warm-up and separate from the calibration. Then the style of the question asking style, which is, I mentioned, this CREST model can be done for warm-up. It can be done for calibration. It can be done for simulation. And we are simulating, so we put simulation there, which is short for simul. Model that we use is a CREST. Routing that we use is KW, stands for kinematic wave method for the routing. The basin is a name we give for this study. Basin area is called KY. Precipitation data, we give a name that is MRMS, and the above, MRMS, right here. And that's why I'm saying you can set up multiple different precipitation data sets and give them different names, and you just leave the bracket over there, and you can change your precipitation data set by just changing name over here, and you don't have to delete or erase anything above. The PET data set is PET. And output, we're going to output to our output folder. Parameter set, we give the name that is KY CREST. And routing parameter set, we give a name as KY KW. And for time steps is what's the time step you want to simulate for this demonstration. In this demonstration, our precipitation data is hourly. Now our simulation time step will put in hourly too. You can put it half hourly, 10 minutes. It's all up to you. That's something can be changed. It can be 10 minutes. Right here we do 1 hour. The time begin of this simulation period, we put it 2022, July 25th, 0 hour, 0 minutes, and the end is the 2022, July 31st, 0 hour, 0 minute. State, that's more advanced use of a CREST model, and we can talk about it in other training periods. In this case, we can delete it. It's not needed. Then the last bracket is execute. It's the same as other brackets that you could also name different tasks and change the name over here to warm up or simul or calibration if you have set up differently. In this simple demonstration, we just do the simul. Now you have completed a control file for CREST hydrological model. Please make sure you save it. And now, let's see. We have a newly saved control file. Then the next thing all we need to do is to double click its executable file. Right here. I double click it. Oh, then it come out, oh, there's some errors over here. Then we can now proceed. We have to change, make sure the error go away. So what's the error? The error is right here, because I put day there. CREST doesn't read day, it only reads D. So I have to correct it and then save again. Close it, correct and set up. You just double click this executable file. Then it will start running. You will see this hour is kind of changing over time. Then when it's done, it will show done right here. That means the simulation is done. Now you look at this output folder right here. The results will be listed here as a CSV file. You double click the CSV and you have this time and date and discharge uh, from your simulation and the observation data from the gauge data that you have. So this is observation, but you probably can see there's some differences here. That means, there's a difference between a simulation and observation. And that's where you need to change the parameters that I just mentioned in the control file to make sure those two things can match in the future. And that will be a future training sessions that you need to make sure the simulation will be as accurate as possible. And thank you very much. I hope you enjoy this video.